And today I wanted to kind of complete the discussion on that we started with the quantum Hall effect, but really that has led in the last 10, 12 years into discovery of new forms of electronic materials that are really designed from the bottom up, from the choice of atoms, of symmetries, the way they are put together in a crystal, and all of that result in trying to kind of emulate the properties where what you could get with quantum Hall effect with large magnetic fields, you get without magnetic fields now. The material itself is capable of showing features that are without an external magnetic field. The hope is we can get precise quantization of conductance or transverse conductance and such, even without external fields. That's kind of the basic idea. This is a materials design problem now, as to how would you arrange a certain number of atoms, and what are your choices of those atoms, such that when electrons move in such crystals, they for example, they are not able to move in the bulk of the material. They only can move at the edges. That's an example. Can you design materials from that perspective? So, and that really started with kind of going back into the history. So the Berry phase is a central unifying concept in these ideas, and we'll see now that materials in which that we can design that have non-trivial or that have finite Berry phases and Berry curvatures can provide you with such features, which are analogs of the magnetic field, right? So I mentioned in the last class that how the Berry curvature and the fact that it's integral over a closed manifold or closed surface, be it in K space or in any space, parameter space, is an integer, right? And that we saw it from the discrete version of it first, right? We looked at it first from this perspective, and then we saw that in the analog, or rather in the continuous version, it's the same deal. You have a finite number of things like vortices, etc., for a vector field on a surface which is closed. The total flux modulo 2 pi must vanish. But if you include all the angles, you will get some integer left over, right? If you divide the whole thing by 2 pi. What we'll do today is try to kind of first make this small connection with differential geometry about looks like it's all quantum, but the aspect that an integral of a curvature on a closed surface is quantized is not a quantum concept. It's a very traditional geometric concept, and goes back to Gauss and others. If you look carefully at your Gauss law for electric charges, it's the same deal. There's a finite number of charges inside any surface area. When you integrate your E dot ds, electric field, right, dot ds over a closed surface, right, that gives you the total number of charges, and there's probably a 4 pi and all that sort of stuff here, right? So this is kind of related to that, the fact that mathematically they are really identical. Okay, and some of the stuff we're going to talk today is starting with some work by Duncan Haldane and others right after the discovery of quantum Hall effect. They were asking questions like, can you actually emulate the quantum Hall effect in a material where there's no magnetic field but it's still showing such behavior? And we'll see how that thought process came about, how Haldane's ideas, how that kind of led to what is today, kind of a very active field of topological insulators, wild semi-metals, and all that sort of kind of interesting new materials that are a result of this aspect. Okay. So first, a very quick connection, in some sense, here to the idea of why integral of a curvature on a closed surface is quantized. And this goes back to, in fact, Euler. I think you have probably seen this discrete version of this in many ways. So if you take any closed object, a cube or a tetrahedron like that, and you count the number of vertices, right, number of edges of this geometric object plus the number of faces, right, and you take vertices minus edges plus faces, right, and what you will get here is for any closed object, solid object like that, you will always get a 2, and that's kind of very interesting. You can take this, that, as complex as you want to make it. Here you will get a 2, right? Number of vertices minus edges plus faces, which is all of them are integers. It's just, and the number will be 2. Right? Okay. So I mean, let's look at one example, if not convincing. So 1, 2, 3, 4. Right? 4 vertices. 1, 2, 3, 4, 5, 6 edges, right? And 4 faces. 4 plus 4 minus 6 is 2, right? And you can try it on all these. You will get always a 2, right? Now, so this was called the Euler characteristic. This number is an integer. I mean, of course, it's a sum and difference of integers, so it must be an integer as well. But what's very interesting is if you poke a hole inside this, like you make this now, then it won't be 2 anymore. It'll be 2 minus 2 times the number of holes in that you have poked into that solid now, right? And this is very discrete version. There is no quantum mechanics in it. It's just pure geometry, right? And this quantity now is called the Euler characteristic. And this was, way before the discovery of quantum mechanics or electron, or in 1600s or something like that, right? And they figured this out, that if you have one hole, then the Euler characteristic will be 2 minus 2 times 1. That's 0. If I have 2 holes, I'll get minus 2 and so on, right? And you can make more holes. And then this is just a very standard geometric property of any object, any three-dimensional object. And there is an analog to this. You can go to higher dimensions, and Poincaré's conjecture, all that stuff is related to that, which was solved in the last decade, I think, right? That any dimension it should hold, and that sort of thing. Okay? So now, so what Gauss did was very interesting. He generalized it, and what he said is, look, what will happen if I don't have these sharp edges, but I have smooth surfaces? So, instead of these sharp edges and all that, sharp vertices, I smoothen them out. I take that and make it into a sphere, for example, right? And this into a donut or torus and that sort of thing, right? So what happens then? These flat surfaces, for example, have no curvature, right? There's no curvature. It's a flat surface. But once you make it into a sphere, there's a curvature now, right? And the curvature is a very well-defined geometric concept, right? Curvature, for example, of a sphere is 1 over the radius. I think you kind of know that. Smaller is the sphere, smaller is the radius, more is the curvature, right? Right. And in a two-dimensional surface like this, which is embedded in three-dimensional space, if you might, there are 2 curvatures at any point you sit, maybe along that, along that, if you want. There are 2 curvatures, 2 directions, right? Really, 2 orthogonal directions, right? And the curvature of a sphere is mathematically the curvature of, or rather, a curvature of any curve was mathematically defined by Newton, which is related to derivatives and the double derivatives. This is a simple form. I'm not trying to write all that down, but for a sphere, you can write down the equation of the surface. Let's say z as a function of x and y, which is in this plane, and you can write it in that way. And then z of x comma y can be written down as if you want, a 2x2 matrix, and this will have a very close analogy to what we are going to do today for the rest. If you look at all kinds of topological insulators, it will be very closely analogous to this, I think. And now you take the curvature, the definition of the curvature, or rather, kappa 1 and kappa 2 are the 2 curvatures that I mentioned. And if you take the product, that's called the Gaussian curvature of a, of any point here. It's called the Gaussian curvature. It's a generalized concept now. So for example, the Gaussian curvature of, if you take the equation of a sphere, and take the curvatures, you'll get 1 over r and 1 over r. The product is just 1 over r squared. It's very simple, right? If you take it for a slightly deformed object like this, then you can see that, for example, in that direction the curvature is a little larger, but in that direction it's a little smaller, right? Regardless, I mean, and the curvature is changing as you move over on the surface. It's not the same everywhere here, right? So as you move on the surface. And but what Gauss proved, which is a very Gauss and Bonnet actually both had contributions to this, is if you take the curvature, the local curvature of any point on the surface, and you take the product and the total Gaussian curvature, and you integrate it over the entire surface, okay? Integrate it over the entire closed surface, then you will get 2 pi times the Euler characteristic here. The Euler characteristic with the number of holes, or the genus of it. Okay? Yeah. And this is what is very interesting about this theorem. It's called the Gauss-Bonnet Theorem. Is that you can take this and deform it as much as you want, but the number on the right is not going to change. So whatever is gained in curvature in some parts will be lost in others, but the integral will be the same. And by doing this, what you kind of now you can go to, for example, a torus, and you evaluate it, and there G is the number of holes or handles. It's 1, so you'll get a 0 for a torus, for example. If you get 2, a pretzel-shaped thing with 2 holes, then you will get -2 and all that sort of thing, right? So some of the interesting things you might notice is the curvature is always positive on this, but if you are sitting on this side, right, it's curving outwards on both sides, but on this side the curvature is negative, right? So if you go from a region of negative curvature to a region of positive curvature, and quite obviously there's a region in between them where the curvature is 0, right? There's no curvature, and I think you can see in this line where is the curvature 0 on the very top surface, because it's curving this way but it's not curving that way. Does that make sense? The curvature becomes 0 in one point, and this has very interesting sort of implications on things like wild semimetals, where you will go from a kind of a Dirac point which has positive, which is there will be regions where you will be guaranteed to have some 0 crossings, for example. We'll see that. So now the integral of this Gaussian curvature on any closed surface in any dimensions now is what's really the Charr number, as we have talked about earlier now. So this is also very much related to the Charr number now, and this is now divided by 2 pi, and whatever is left over is it's closely connected to the Euler characteristic, is what I'm trying to kind of say that here. But the Charr number is defined not just for the physical curvature of this, but if you actually put a vector field on it at all points, right, and the vector field is changing, let's say, right, then the Charr number is defined for any vector fields. It's not just the geometric surface curvature of the surface. Now that's very interesting, because you can imagine, for example, let's say a vector field on top of a surface like this. Maybe you can think of vectors that are maybe radially sticking outwards from like a hedgehog. It's sticking outward at all points. Okay. And the Charr number for a vector field is physically the following: that if I take let's say it's a very simple example really, that I'm taking a vector field associated at each point on the surface, okay, and that's pointing radially outwards, right? And what I want to do is I want to kind of comb these vector fields and bring it in the plane of the surface. Does that make sense? I'm just going to take those and trying to kind of smoothen out and bring them, for example, onto the plane of the surface, comb them down, right? You can think of them like that. And what the Charr number says is, if you try to do that, if you try to pull the vector fields down and then try to do that, there will be at least, for example, in this picture, there will be at least 2 points where you cannot do it. There will be vortices. Does that, can you see that? Basically, if I try to kind of comb everything this way, you can see that there will be some stuff that will kind of stick out and it won't quite kind of fit here. There will be some stuff that will stick out and won't quite fit here. The rest will. And these are the two vortices. That's the Charr number physically, or of a vector field, for example. It's kind of, I think it's very close to what it actually is, because typically in a right. Okay. So that and then that argument also goes as to why on any on the surface of the Earth, there's always a couple of places where there are cyclones going on. I mean, you can't avoid it because the wind is a vector field, and there'll be some points where there will be. And it's the same reason you have your little tip on the hair, where you cannot, comb it around. It's the same reason, really. There's not much difference to that. Yeah.
Is the Charr number equal to pi?
No, the Charr number is always an integer. Say that again. Is the Charr?
So 2 pi.
It's divided by 2 pi.
Right. So therefore, if you compare it to above, it's just going to, well, Charr number is equal to 2 minus 2g, right?
Charr number is exactly right. This is what I would call the Charr number for this particular Gaussian curvature. But to be more exact, the Charr number is defined for that vector field I was mentioning. It's not the local curvature, geometrical curvature, but the if you define a vector field on this surface, that's what the Charr number counts.
So different vector fields can have different Charr numbers on the same surface, right? It's possible.
Oh, absolutely. Yeah. Oh, exactly. So if I have different vector fields defined on the surface, this is what I wanted to kind of say, fine print was, this is one example of a vector field. There can be other vector fields too. So for example, I can have the Charr number may be 0 here. It looks like 2, but it may be that this tip is going this way, but here the vectors have to go in, and then one is a positive sign, the other is a negative sign. They'll be 0. But it is right. So the Euler characteristic is a very much a geometric concept. That has not much to do with the vector fields at all. So it's just and Gauss really liked this sort of picture very much, because what this implies is if you, for example, are an this led to what he calls himself. As you know, Gauss is credited to have discovered a lot of things in mathematics, but according to him, the most remarkable theorem for him was the fact that on a closed surface like this, if you are an object living on a closed surface like this, but you cannot see very far, meaning you cannot see beyond a very local region around yourself. The question one may ask is, can you say how many, what's the nature of the surface, how many holes there are, is it a sphere, is it a torus or something like that, without stepping off from the surface? Because if you step off, you can obviously see it, right? But according to this, if you kind of find the curvatures everywhere, or if you go back to this picture and you count the, create a lot of these patches, and you create, calculate this number, you can calculate how many holes there are. You can conclude from there. You don't have to step off the surface. Does that make sense to you? Meaning, I can find, for example, the total curvature, or I can find the total, curvature of any surface. As a result, I can conclude what is the overall topological geometry of the object I'm living on without stepping off the surface. Was that?
I know if I'm living on a closed scale on Earth.
Absolutely.
Or if I'm living on like a donut.
Exactly.
Or if I'm living on a flat surface.
On a flat surface. So, for example, on a flat surface, the curvature would be 0 always, wherever you go. But the catch is obviously you have to cover all patches. You can't leave anything out, right? So you have to do everything here. And again, this didn't come about from nowhere, because Gauss was involved in. He was commissioned, I think, by the ruler at that time to draw maps, and and then he tried to reduce his work because in the maps you have to show curvatures of valleys and hills and all that. So he concluded he used this to kind of reduce his work as well. So yeah. Okay, so a classical manifestation. So there are a lot of very interesting aspects of this as well, which I'm not getting into. A classical manifestation of that is here's an example. If you take light through an optical fiber, an optical fiber. This is classical electromagnetism, where you can see the very phase. And the electric field is perpendicular to the momentum. The light photon is going this way, and the magnetic field is this way. So E cross H is the magnetic. Yeah. And then if it goes out this way, then there's no problem. The electric field comes out as it was. There's no change, right? But so you can kind of track, for example, the k vector of the photon or the light as it goes through, and it kind of stays on at a point. It's always pointing in the same direction, right? K vector. But if I take the fiber and I kind of loop it around a few times and I come back again, make it parallel here, then what happens is the light will propagate such that the k vector is along the axis of this fiber, right? And so the k vector now starts changing, right, direction as it goes this way, and then it turns around and goes back and goes back again, right? And as a result, the k vector, if you sketch it, it traversed a path. The tip of the k vector traversed some path in the sphere on the surface, and when it comes out, it may actually, depending upon the angle loops and all that, it will come out at a different angle now, right? And that aspect, that is essentially also related to what we are calling as our Berry phase, which is it remembers the curvature of the surface it went over, if you might, right? And in fact, the angle that you will get here is related to the solid angle this patch subtends at the center of the sphere. In fact, I think it's right. So it's related to that. And this was discovered in optics actually in 1960s by Panchratnam, and so he already had seen experimentally what later came to be known as the Berry phase. The Berry phase has obviously a very strong connection to quantum mechanics. So this is a classical aspect of the Berry phase. You can do quite a few other experiments. Here's an experimental measurement, a little more recent perhaps, 86, where they're trying to measure the Berry phase based on how many times this optical fiber loops around a cylinder, and they're changing the winding of the k vector of the light, for example, and they can verify the Berry phase experimentally measured stuff. So now I wanted to kind of say that what I wanted to show now is that the Berry phase has a so the quantum Hall effect we talked about is where the Berry phase was achieved with a large magnetic field. And we kind of didn't really try to say exactly what is the Berry curvature, except we related the conductance, right, the transverse conductance to the Berry curvature, and then just made use of a very nice theorem that what we wrote was that transverse conductance is equal to E square over H times an integral of the Berry curvature in the K space times the, if you are in two-dimensional space, something like that. And what we said was, this quantity is an integer given, this, we already proved why the sum of, the flux is, Berry fluxes over a closed surface should be an integer, right? Divide by 2 pi, sorry. Okay, that will be an integer. And that's how we said this guarantees that your transverse conductance in this situation is going to be an integer, and that gives you the integer quantum Hall effect. But physically, what really happened was you took a two-dimensional electron gas, and because of the magnetic field, you created these, discrete sort of Landau levels, and your Fermi level, you put it here, right? That's what we are doing with transport. Fermi level was put here, filled band, empty band, right? And somehow, all these filled bands, the traditional conductance is 0, because in a filled band the total conductance rho xx for them was 0 because, it's a filled band, right? Equal number of group velocities plus and minus sides and all that. But rho xy is not 0, and we achieved this because of a magnetic field, right? And this is kind of the key point here. This is h bar times the cyclotron frequency, which is E times magnetic field over m star, right? Does that make sense? I mean, so this is we have achieved with a magnetic field. And what we want to really do is, as I mentioned earlier, today we want to create materials where you don't have to apply the magnetic field and still get something like this. Right? So that's really what we want to do. And then that would be obviously nice for many transport phenomena and perhaps might even have some uses. And how would one go about doing that? So let's first do a little dissection of what does the magnetic field do. And this is a real magnetic field. What we are going to manufacture is a material where there's effectively a magnetic field, but in the K space. By designing the lattice symmetries, the way the atoms are created, we can design the K vectors that are allowed for the electrons, right? And then we can manufacture, based on the material choice, what you call as a quasi-magnetic field or a magnetic field in the K space, and that's your Berry phase, really, right? A Berry curvature, that's what it is. Okay? So let's first look at what does the magnetic field really do in quantum mechanics to an electron, because in the end we are interested in influencing the transport properties of the electron, right? I mean, that's our main goal at this point of time. So let's see, if I look at an electron and I place it in a magnetic field, let's say any direction, but you can align the magnetic field along the z direction if you as a general case, or you align your z axis along the magnetic field. There's an electron. So what are the energies allowed for the electron? Well, you again go back to your Schrodinger equation and say that I write down my Schrodinger equation for the electron and write psi is equal to E psi, right? Except when I apply a magnetic field, I have to do a couple of changes here. I must change my momentum, right, to the momentum. The way the magnetic field enters Schrodinger's equation is it becomes P minus electron charge times the vector potential, such that the vector potential cross is the magnetic field, right? That's how it enters that. And once you do that, and you bring in and you kind of expand this out, etc., do all that business, what happens? So let's call this part, just the one without the vector potential as H0. Okay, and when you do that, you get these extra terms here, right? This and this, and these are related to the magnetic field. Right, sigma is a Pauli spin matrix, by the way, and all that. So I just wanted to kind of write that down first, because I want to first see what it does to the wave functions, to the eigenvalues, right? Let's say this electron initially, in the absence of a magnetic field, had energies, just E0, okay, whatever be it. It was sitting maybe in the ground state of a hydrogen atom, and it had energy E0. But we know that it could hold both up and down spins, so really there are two. There are two states at the same energy. They're degenerate, right? And once you apply this magnetic field, what the Hamiltonian changes to is, first of all, what happens to the wave function? The wave function for a hydrogen atom without spin is a scalar quantity effectively, right? It's just it's a complex number, right? But the moment you apply a magnetic field, it splits into what you call as a spinor. It's a two-component function now, right? The wave function becomes wave function with upspin and a wave function with downspin. There are two components, and you write it as a vector, right? So that's the first thing that happens. The Hamiltonian now becomes whatever was original Hamiltonian without the spin plus. Let me write this down, and we will so sigma dot b. So this is called the Bohr magneton mu b. Okay. E Planck's constant over 2 mass. Okay. And then you may have some other terms here based on higher order effects, etc. I'm going to forget that for now. Okay. Is equal to energy times psi up and psi down. So that's your new thing that happens once you apply the magnetic field. Right? Now, if you try to find the eigenvalues of this, then physically what happens is if my magnetic field was 0 till here, and I turn on my magnetic field, then it splits like that. One energy goes up, the other energy goes down. And the reason for that is from here, and I'll actually just show a simulation. But remember, what is this physically? It's sigma x times bx plus sigma y times by plus sigma z times bz. What are sigmas? They are the Pauli spin matrices, 2 by 2, and that this is a 2-component, so it's all consistent, right? Everything has 2 rows, right? And this is just the amplitude of the magnetic field in the x direction, the amplitude of the magnetic field in the y, and amplitude in the z in Teslas or Gauss, whatever you want, right? So now, if you have only the if your magnetic field is only along the z direction, then obviously you just have that, right? Right, sigma z. If you go back and look at what is sigma z, that is 1, 0, 0, minus 1. Okay, that's just that. And so that becomes bz and minus bz. Forget that. And because bz is equal to total b, we just write it as the magnitude, right? And times the magnetic field, times the Bohr magneton, which is sitting as the coefficient here, right? So that's your extra term, if you might, to the ordinary Hamiltonian that you had. So that's your extra term here, right? So this term, what are the eigenvalues of this term? Right. That's the right? Yeah, E0s. And so you get E0, and then because of this, you can see you have a 2 by 2 matrix, you find the eigenvalues of this. So essentially what you have then is, let me write that down, E0 plus mu b and E0 minus mu b, and done. There's nothing else left, right? The 2 eigenvalues. So what are the 2 eigenvalues? This one is E0 plus mu b, Bohr magneton times that, and this is just E0 minus mu times b, right? And the splitting is twice mu b. So with the magnetic field, you are able to split the eigenvalues. It's just a very standard, this is the explanation of the Stern-Gerlach experiments, which first discovered that there's some spin in materials and all that. And that's what led Pauli to introduce the spin matrices in the first place. Now, what is interesting, I mean, if you look at the structure, just stepping back a couple of things here, is the way we ended up doing this is we have a, let's say 2-level system like that, and then you had plus some number, and here it is mu b times 1, 0, 0, minus 1, right? That's what we did just now. I'm just repeating the same thing. And let's just generalize this concept a little bit and say that whatever I put here, okay, is, I'm going to call it as del over 2, where del is the gap, 2 mu b, right? This is a gap between 2 states, right? Does that make sense? So if I write whenever I can write my Hamiltonian of any system, right, as, let's pull that out, that's also a Pauli matrix, except that is the first Pauli matrix, so that is E0, right? If you look at this, we can call it, well, this is just the identity matrix 2 by 2. Now this is sigma z, right, for Pauli matrix. So I can write my Hamiltonian as, let's forget this quantity now, rather not forget, I'm going to just write it as sigmas, okay, plus sigma z, E0 times 1, plus that, okay. If I see a Hamiltonian, if I see a 2 by 2 matrix and I can put it in this form, if I can decompose it into identity and a Pauli matrix, whatever sits here is half of the band gap of that region. That we can say right away, right, from this picture, okay. And there are two other Pauli matrices that I have not shown here, not written here, but let me write that down. For the most, I'm just kind of trying to generalize this, and the reason for that is I need this sort of understanding to explain a lot of the TI stuff we'll talk about today. Okay. So and then I have 2 other terms here. Let me write it as sigma x and sigma y. Right? There are 2 other terms. Let's say I had a magnetic field in the not in the z direction, but in some xyz plane, right? In which case I will have some terms here as well, right? But whatever I have here, I can parameterize it and write it as the coefficient of x, some function here, which is related to x. Rather, I write it as h sub x. Just let's write it like that: h sub x, and this is h sub y. Okay. And instead of this physical gap we talked about, let's write it a very general form: h sub z. These are just functions of whatever parameter here. It may be a function of the magnetic field. It could be something like that, right? And we'll graduate it to make it a function of the ek diagram very soon. Okay? And finally, why leave it here? You also make it as h sub 0 as a most general function. This is the most general Hamiltonian, and the most general 2×2 Hamiltonian. Any 2×2 Hamiltonian, you can always write it like that. And the reason for that is these four vectors, these four matrices, 2×2 matrices, span all of 2×2 matrix space. No matter what 2×2 matrix you have, you can always write it as a linear combination of these four. And that's the nice thing about Pauli matrices. Okay, and this is in your assignment problem for 4.5. I've asked you to kind of look at it this way, so that you can now write your total Hamiltonian as h0 times identity plus hx, hy, hz, and in a more simpler way, you can write it as, in a more compact way if you might, h0 times identity matrix plus, this, you can take these three quantities and call that, well, I'm going to write the triplet as a vector. It's very so and write it as that vector, dot product with what's called the Pauli matrix vector. This is very compact way of just writing this thing. Does that make sense? Where this vector is hx, comma hy, comma hz, and this is just the sigma x, comma sigma y, comma sigma z. Right? No problem with that. It's dot product with that. Right? Is that okay? No? Okay. So now once I can write it like that. I can't find a pen working today, so yeah. You can now ask what are going to be the eigenvalues, the eigenfunctions, all that sort of business with it. And let me explicitly write this function, the total Hamiltonian, down here. It looks like h0 plus hz from here and from here. And it will look like h0 minus hz. It will look like hx minus I times hy, and hx plus I times hy. This is the structure of the matrix. And this spans every possible 2×2 matrices. And we are going to apply it now to various cases. Graphene, we'll gap it, see how the Berry curvature comes about. We'll apply it to a topological insulator, and you do things like wild semi-metals. All of them follow this same strategy now, right? So once you look at this and say, I can ask a question now, what are the eigenvalues of this Hamiltonian? And that's actually very easy, because you look at this vector, okay, when you didn't have hx, hy, it was just plus minus hz, right? Right? And now it will just become plus minus square root of the magnitude of this total vector, hx squared plus y squared plus z squared. That's what it's going to become now. I can show that in a couple of steps. This is a question? Yeah.
Yeah. What's the first term in the Hamiltonian? H naught times what?
Oh, this is an identity matrix. One, so you can call it the, it's basically 1, 0, 0, 1. Yeah, it's. I'm just writing it as a more, big one here, with a 2 as a 2×2 identity matrix. That's what I wrote it as. Okay. Okay. Just as an rather not demonstration, but if you are going to use, you can use programs like Mathematica, and it has all this stuff built in, MATLAB or whichever. So for example, I'm just going to show that. So it has built-in spin matrices, Pauli spin matrices. You can just call Pauli matrix 1. It will give you sigma x, sigma y, and all that. And the 3 Pauli spin matrices are as shown here. So sigma x, sigma y, and sigma z. Right? You can take products, all that stuff. When you take products, for example, Mathematica or MATLAB, I think you have to give specific commands. A product is a dot at the bottom here, for example, spin sigma x, sigma y, and these are, if you multiply sigma x, sigma y, you get I times sigma z, and so on. You can also do nice things. You can do matrix. You can take exponential of the Pauli matrix, and all that stuff is no problem. It will easily evaluate all that stuff. Okay? So now you can say, well, give me the eigenvalues, and that's, again, I mean, nothing very fancy, but we just kind of wrote that now, and here's the splitting with the magnetic field. Okay. Now, whatever we are getting here with the magnetic field, what I wanted to kind of say was the search for materials like topology, insulators, etc., started by saying, how can I emulate the same physics but without the magnetic field? And the whole game, here's kind of most of topological insulators in one sentence, right? Is you create your terms, these 4 terms, using the EK diagram, okay, where K is our Kx, Ky, Kz, depending upon 1, 2, or 3 dimensions, okay? And then find ways for the K's to emulate the magnetic field, okay? And create situations where the vector, the vector Hx, this vector here, has non-trivial Chern numbers. That's really the game. And I'll talk about what is exactly the Chern number, or has non-trivial Berry curvatures. This vector field should have some Berry curvatures or Chern numbers, and then you are in the game. You have some topological or new interesting properties like anomalous Hall effect, where you don't have an external magnetic field, but still the carriers are kind of going to the left, and that comes about whenever you have that such sort of a situation. That's kind of the game. You kind of design your material such that you get the properties of the magnetic field, or in other words, without the Bx, By, Bz's, you replace them by Kx, Ky, Kz, and some functions of them. So that's really kind of the game. Okay, so let's see that in action, perhaps, and we'll to do that. One of the first things I wanted to kind of do was look at what happened here. Look at graphene, because that is the first place where you encounter something that looks, kind of suspiciously like the magnetic field, but not quite. Where what we'll see is in graphene, as I change the K, my energy will go linearly again. It'll split linearly, except it'll be in 2 dimensions. It'll be a cone. So that's kind of the first place. You say, well, I can emulate what magnetic field does, but with a K field, without a magnetic field. Of course, you can also apply a magnetic field on top of it, but the K already is doing something like the magnetic field. That's kind of the first thing. One of the things I want to kind of say is I can take this H vector and ask for how, so in a 2 by 2 case, it's very simple. The eigenvalues are plus minus that, okay? So it's plus minus that. And you can see that if you go back and look at what we defined as the Berry curvature depended on the difference of the eigenvalues, okay? E1 minus E2, meaning the difference of the eigenvalues. Okay? And wherever the Berry curvature, wherever the eigenvalues meet, become degenerate, it blows up. But it actually has a finite integral around that region, and it's always what is that integral? It's always going to be defined by the Chern number. It's an integer. It could be 0, but it could be 1. It could be minus 1, right? So these points of degeneracy are of very high interest because they are the sources or sinks, if you might, of Berry curvature. And then we are going to kind of keep that in mind. Or in other words, where do you have degeneracy? If you look at this picture, maybe you can tell me what is the value of H where you have the degeneracy. This vector must be exactly equal to 0, right? Wherever this vector goes to 0, you have basically a kind of a monopole, if you might, or a Berry curvature blows up there, right? And that means you have something interesting topologically there at this point. Yeah.
Would that be related to like when you're trying to like put the vectors on the surfaces?
Absolutely, it's exactly related to that. Yeah, yeah. Meaning, if you look at the eigenfunctions around those points, you'll see that they form vortices around that function. Exactly right. So, okay, and in addition, what that does is Berry curvature from this picture. Berry curvature will give, if I inject electrons, that are going along the x direction, and it encounters a Berry curvature of a certain orientation, maybe this way, then the carriers go this way, or they get an anomalous, or rather they get a sideway kick, if you might, right, and it give you a sideways conductivity. Wherever I can manufacture such cases where I take this to 0, right, wherever they meet. If the carriers go around that point, they will. Again, this is probably also fair, reasonable argument. I think we can do wonders if we had pens, but it just could I request somebody to just look under neighboring rooms if there's a pen? I just think it will be good if I have one. Yeah, thanks. So really the idea is remember this what we are trying to do this is in K space now. It's not in real space. Let's go and look at the real calculations before we go forward. Actually, one more thing before we go. This term, the original Hamiltonian also has what's called the crystal potential. If you are in a crystal, this is the crystal potential, right? And that potential can also help shape. It can interact also with this term. There can be a coupling of the two. So this term, once you put electrons in a crystal, they have a certain orbitals. They have to satisfy some orbital directions and crystal symmetries, right? The wave functions. So this is called the orbital term, and this is the spin term, right? And when the orbit also controls and interacts strongly with the spin, you have a lot of spin-orbit coupling. Spin orbit. So spin possibilities are also shaped by the orbital possibilities of this. Thanks. So that is another kind of tool in our toolbox to influence these things here. For example, you may not have enough juice to actually create just from the from this term what you want. Then you can go back and look for this term a little bit, in spin orbital terms as well. So, yeah. Okay, so let's look at graphene, because that's a good example, I think, to look at. So I told you quite a few very general things initially, and now I want to make things quite a bit more specific. Okay, so I just want to see what are the things I want to cover. Spin orbit. Okay, so we want to go from real space Berry phases to momentum space Berry phases. That's kind of the game we want to play. So graphene is a good example. So let's look at graphene. We first want to write down the energy stuff for all the Hamiltonian stuff for graphene, identify all these things, and say does graphene have a Berry curvature? Does it have a Berry phase? All that sort of business. So and then what can I get? Sigma xy's, topological properties in graphene. So what is again? So physically. Why am I using the old one? Sorry. Is this one? Yeah, yeah. So physically, graphene is. This is nice. So graphene is carbon atoms, right? And they are in a honeycomb lattice like that, and so I want to draw the lattice and kind of outline the whole. Method how one might go about designing a topological insulator material or something like that. Okay, so let's call this if you're sitting on these atoms, if an electron is sitting here, I can see that this environment is not the same as that environment. The chemical bonding here slightly different geometrically than there, right? Bonds in different directions. So this we call as a sublattice or A atom. This as a B sublattice, and graphene. So these two together is the basis of graphene. Two atoms, A, B. They are the same atom, carbon, but 2 atoms of lattice. And the repetition is, sorry. Okay, so now if I'm an electron sitting here, I can hop, from here, for example. By the way, so and you can take 2 vectors as the A1 and A2 as your lattice vectors now, right? And minus of A1 plus A2 will be that way, and that you can also consider as another vector, so in this picture. So what is the Hamiltonian for graphene for electrons? So here's my lattice. I've designed a crystal, let's say. Of course, with benefit of hindsight, we know the shape of graphene. But let's say I'm trying to go through this and say I have 3 vectors A1, A2, A3, and I have these atoms. If an electron sits on this atom, let's call it an energy E0, right? And if it hops from one atom to the next, let's call that as minus T0. I think we have done that before, and we write down the Hamiltonian for this whole system. Then try to go to the eigenvalue space, and then we connect to this picture again, right? So for example, here I'll have E0 times C, which is the creation annihilation operators for electrons now, which is fermions, at say site A. So C site A, and say I index them as n. N is the site number here, and this could be n plus 1, n plus 2. Typically, it will, 2 dimensions, 2 numbers, but I'm just labeling it as 1. It does, I know, not. So, and then I say C A, comma n dagger. So that's how many. That's the number operator for this site, right? And then if it's sitting on this side, that's the energy. Right? Similarly, you'll have something for B. It's exactly the same, right? Right? And then you will have all these hopping terms now, right? Minus T0 that, minus T0 that, and all that sort of thing, right? So maybe I can write it like minus T0, and you can perhaps see that it can hop from cross lattices from A to B, right? Or B to A, nearest neighbor hopping. It goes from here to there, then it goes from A to B site. Right? So you annihilate in A n, and maybe create in B, comma n plus 1 or n minus 1, wherever you want to go. Do you see that? I mean, that's what's going to happen, right? And if I'm sitting here, it can hop to 3 nearest neighbor sites, right? So there are 3 of those. Minus T0. I'm not writing them all now. So that's my Hamiltonian for any site n, and of course the total is overall is just sum over all, and that's your total Hamiltonian. This is very standard tight binding stuff that we have done before, right? So, yeah.
For the hopping term, why is it CB dagger CA, and why is it different B and A?
So yeah, if an electron is sitting here, right? Look at the nearest neighbors. If it's sitting in A, or let's say it's sitting here in B, okay? Maybe because that term is, so let's look at this electron. It's sitting here. So it can hop either there or there or there, right? But when it hops, it starts from A side, but it ends up in a B side, right? So that's why it's just a mixed stuff here. So now, once you have written down the tight binding Hamiltonian with the nearest neighbors, how do we go about going to find the eigenvalues? We typically go over to K space because it's a crystal. You know that electrons are delocalized, so you want to find the K space picture, and you do the C. Let's say C A comma n. This is the creation operator. You write it as sum 1 over square root of n, which is a normalization factor, total number of sites, times e to the power I k times xn or rn. Here it will be 2-dimensional, so I should be a little careful. It's a 2-dimensional crystal, okay, k dot rn, okay, times c a comma k, where I'm making a transformation from creation operators in real space to creation operators in K space. Right? So this is a Fourier series. And I think you have done this in your earlier assignments, right? And then you can go back and look. We also did some of it in the superconductivity, the Bogoliubov-Dijen sort of pictures. And then similarly, CA, and dagger will have a minus and all that. So once you plug in all that, you see there's also the Rn, which will remember which lattice site you are on, what the lattice constants, all that business. It will remember all that stuff. And when you come back, your Hamiltonian in K space is going to become diagonal, right? And the way it will look is CA, K dagger, CB, K dagger. I'm just kind of writing not going through the entire process here. You could have probably guessed how if you draw an analogy to that picture, but let's write that down without making those guesses. So, so it will look like this. You'll get an E0, which is the on-site energy, and E0 as on-site energy. And you'll get a minus T0 times e to the power I k dot A1. This is one hop to one side, plus e to the power I k dot A2 plus e to the power I k dot A3. This is your three terms, hopping terms, right? This is what you're going to get. And then this thing here, it's a Hermitian matrix always. So this is just the complex conjugate, meaning all the e to the power I k's become e to the minus I k's. And this is just the k at any k, for all k's, this is the, for any value of k, this is Hamiltonian. And so the total Hamiltonian is really you sum over all k's. Just like you summed over all n's, you sum over all k's. Now this is the Hamiltonian of the entire energy of graphene, and you can take this now and make a plot of the energies. If you look at the total eigenvalues of this quantity, this term here, this is how the expression looks. So now E0 is what we call as the Fermi energy here. This is the Fermi energy. Plus, here's how k is dependent. Remember, it's two-dimensional, so it's kx and ky. This is how it looks. And all these parameters here, gamma naught, these are combinations of T naught and lattice constants and all that. So based on what is the hopping term, what is the lattice constant, that gives you the strength of this term, gamma naught, for example. So if you make a plot of this, then it looks in K space, it will have a conical structure, and there are two cones in two different points in K space. Remember, this is a two-dimensional system, kx, ky, right? And the points meet, the two bands here meet at 2 points. And now, what are the scales of energies here? So basically, there are obviously other kinds of structure far out, and you have like a ATV. So, but around this Fermi level or the Fermi energy, these are really very good approximation to a very good approximation of perfect cones in K space. There are two of them. In K and K prime point, this is a full, more like a DFT-ish band structure with more bands. Actually, not even. Tight binding is pretty accurate for graphene already. But anyway, the point is in K space, if you go from along a K direction, they are meeting at some point. It's a point of degeneracy. So now you can now most of the electronic transport properties are not going to occur over entire K space. They are typically going to occur in a very small energy window around the Fermi energy, and the Fermi energy is right here in pristine graphene, undoped. Fermi energy is, meaning when you also count carbon comes with a certain number of electrons, you fill up bands, and then you run out of electrons still here, with the 4 electrons per carbon valence, and this is where the Fermi energy of graphene lies, right at that point, and that's called the Dirac point, primarily because if you look at that equation, it looks like a Dirac equation and such. Okay? But now what you do is, instead of trying to write this whole expression, you go to those points in K space, this point and that point, and you expand for small k's around that, very small k's around that. So you take this expression perhaps, or kind of expands for small k's around that. And what happens then is kind of the most interesting aspect is your Hamiltonian looks like this. And I've taken out the Fermi energy here. I've subtracted out the Fermi energy. And you look at this structure, And there's something called a Fermi velocity, which is just a combination of hopping terms and lattice constants and all that sort of thing. This magnitude is about 10 to the power 8 centimeters per second of the Fermi velocity. Lattice constant and hopping terms. But you look at this, and you look at this term, looks very similar. These things are 0 for graphene here, right? But you see it looks like kx minus iky and kx plus iky. You need a hx plus ihy, hx minus, right? Looks exactly the same, except now these h values have been replaced with k, which is the momentum, the crystal momentum, right? So now you can write it as sigma dot k, and as we written before, or k dot sigma or sigma dot k. And sometimes this is a dimensionally correct. H bar times velocity times k is actually energy. Sometimes you can throw that out knowing that I can put it back in again later. So then that's okay. So now if you plot a structure of this, so what we saw is it has some degeneracy. It has degeneracy in the K space. Okay, I can now ask, well, is there a Berry curvature? Is there a Berry phase associated with those degeneracies, right? Because anyway. So okay, and what you will get is you can, because you know the entire band structure, you know the Hamiltonian. Actually, let's forget the mass term here. This is kind of the graphene Hamiltonian. Now, in this paper, they, instead of writing kx and ky, they write it as qx and qy. It's the same thing. And forget the tau z for a second, but kx times sigma x and ky times sigma y will give you exactly this thing, right? Because that's how we got those two. These terms come from that and that, right? So yeah. And so forget this fact we're adding a gap here. Actually, why do that? You can actually even generalize it a little further and say that what if I had a situation where I had a slight difference in energy if the atom was sitting on A side or in B side, very slight difference in energy. Right. What will happen then? Where will that enter? It will enter here, plus that difference. Let's call it delta, and it will enter here. Right. On-site energies. These are the on-site energies, right? Right. And now you can see that is going to lead to a sigma z term, because that's this, right? And that's why it's written like that here. Let's assume that there's some sublattice asymmetry, inversion, broken symmetry. As an example, if you do that, you can also calculate the band structure of boron nitride, which is indeed two different atoms, boron and nitrogen, hexagonal, and it's this, also a 2D material. So, okay, so that's your Hamiltonian, and once you have your Hamiltonian, you know all your eigenvalues, right? And from there we can go back and apply an expression like sorry, I'm just stepping back a few slides here. You can go here, and this looks complicated, but really if you take derivatives of this with kx and ky and ky and kx and divide by the difference of the eigenvalues, this is the Berry curvature. And so we calculate the Berry curvature based on this 2x2 model, and what we get is this expression. Depends on the gap. Q is the qx squared plus qy squared, and these are all hopping terms, constants, etc. Here's the Berry curvature, and here's a plot of the Berry curvature. Remember earlier on I talked that it should have units of square meters, or square of length, and that's what it is. So in 2 points where the Dirac points, where they cross, or if you have a gap, they don't quite cross this. But in one of those points, it's negative. The other point is positive. The curvatures are different, and the total curvature over the entire Brillouin zone is 0. But they're not 0 in different values in different case points. As a result, what happens is if I take electrons, for example, and so here's the Berry curvature, and when you integrate this Berry curvature over this window, for example, okay, this, and divide by 2 pi, you will get a 1. Here you will get a -1. And you can now let the gap go to 0. completely, and then this will become a negative delta function, and that will become a positive delta function, and the area will not change. It will, and then those are the Chern numbers. If you might, you will get a +1 here, or -1 here, and a +1 here. That's the physical meaning of it. Now, physically, what does it imply? If I actually take this structure, a gap structure, and I inject electrons into it, then electrons that are in this valley in K-space will experience a sideward kick, sigma x, because of the transverse conductance term, right? But it'll experience because the curvature is in one direction, sigma x has a certain the Berry curvature has a one orientation, it will go maybe to the left, and the carriers in the other valley will go to the right. So that's the physics. So you can split the valleys using, if you inject carriers of one valley will go to the one side and the other to the other side. So you can maybe have a valley filter like that. So this was theoretically predicted for a gapped graphene system, and I think a couple of years ago, Professor McEwen's group, they actually measured this not in graphene but in a chalcogenide crystal where it follows all these properties. It also has Berry curvature and all that sort of thing. You can actually measure this. So, yeah.
If these points where this happen are kind of spherically symmetric, so how could you?
So this is a two-dimensional surface. Graphene is
circularly symmetric. They're like 3K points that are.
Right. So actually, yeah, the Brillouin zone is a hexagon here, and there are only two distinct. There are only 2 points because it's shared between 3. So the minima occur at the edges of the Brillouin zone, at the tips here, and that tip is shared between this Brillouin zone, another, and another. So 3. So actually, there are only 2 cones in in the first Brillouin zone. There are only 2 Dirac cones.
Okay.
Yeah.
There are only 2 directions. Like it seems like.
No. There are.
I see what you mean, but like.
There are all directions. Okay.
I guess what I mean is, how could you measure a voltage in a certain direction?
Okay. Right. So sigma. So there are two k vectors in a two-dimensional system, right? Kx and ky, because the electron can move either in kx or in ky, right?
Yes.
Right. And we are saying that we are looking for sigma xy, but without magnetic fields. Right? Right, and what this is saying is you can get a valley Hall effect like that with no magnetic field. And so physically what we are doing is we are injecting carriers, okay? And when I inject carriers, well, I have carriers that kind of are going in all directions. Maybe that's what I'm trying to get to. But if those carriers go into this valley in K-space, okay, those carriers, for example, will gain an additional velocity in that term, anomalous velocity, if you might, if they are in one valley in the K-space. But if in the other valley, they will gain anomalous velocity in the other direction. And when you sum all of them, okay, in one valley, the net velocity will be that way, because the direction is always the same. It's not changing. And the reason for that is if you go back and look at sigma xy, that is related to stuff here times electric field cross the vector potential, right? And electric field is just along the x direction, okay? And vector potential is actually along either plus z in one valley or minus z in the other valley. So it gives you either this way or that way. You split it.
Okay.
Yeah.
But then if these are supposed to be delta functions in graphene, then it seems like this would be a really, really small effect.
Yes.
Okay.
Oh, by the way, no, the fact that just 2 things. One is this effect is not very strong in graphene.
Okay.
But the fact it's a delta function doesn't let you conclude it should be a small effect, because okay, so actually, unless if your carriers are at different k points here, if it's a delta function, that means the graphene has no Berry curvature till you hit that Dirac point, and then you get it. So you're right. So if you sum over all carriers, then you have only like one state pretty much, right? In that case, that's exactly right, that you won't see it much at all. But if you have something like this, which really happens in molysulfide and others, then you have a lot more carriers that experience this anomalous term. So you kind of get that. Yeah, good point. Yeah. Okay, so now, basically all this stuff you can kind of, what we did for graphene carries over to many other materials now. In fact, the same idea, of that we can do tight binding and we can create my Hamiltonian, and then look at Berry curvatures and Berry phases and all that by comparing it to this Pauli Hamiltonian, right? Comparing this thing to Pauli Hamiltonian, and then from there you can calculate whether it has anomalous terms, whether it has spin Hall terms, anomalous Hall effect, all that sort of thing. I've asked you in the assignment to look at the anomalous Hall effect, very similar to that. I've given you a Hamiltonian, you just map it to this problem, and you will kind of get most of the answers from there. Now, whatever I'm saying here, we did it for graphene, but it's true for, you can do it for 1D, 2D, 3D, whatever be it. When you go to higher dimensions or lower dimensions, all that changes is the nature of this K. It becomes either just K, Kx, or Kx, Ky, or Kx, Ky, Kz. Regardless, what I'm trying to say is you can always write a 2x2 Hamiltonian like that. It's just that these functions now have more K's to deal with. It gives you more freedom to make more kinds of materials as well. Okay? Yeah.
Maybe it should be. I'm not. This comes from the math. You can see the Berry curve change, but I'm not seeing from an intuitive or like a geometry perspective why the curvature changes in graphene in this case.
Right. So remember, so the Berry curvature is a property of the band structure, okay, and the eigenvalues of the band structure. I have not plotted the eigenvalues, eigenfunctions of these K states, but I'm guessing, if you actually take the eigenfunctions of these states, which, are basically it will look like e to the power I theta, some I phi 1. I had it written down somewhere, I think, earlier. Yeah, here's an eigenfunction of a very, it's a 2 by 1. It's a two column vector with two components, and you take this and you plot it as a function of theta, which is the angle in the xy plane, and you plot it for various thetas, and you will see that it will form vortices around the Dirac points. That's one way to look at it, and you can actually you'll see it. And in one valley it will go like that, the other valley it will go the other way, so if you plot those vectors, and then that's the physically we can right. Okay. Right, so we are actually unfortunately out of time, because just the next step from here is we can go to 1D, and we will be able to look at the topological insulator, but I think I don't want to take more of your time today. We are done for today. Are all of you going to be able to make it tomorrow? We just have a summary class, but I can spend maybe first 10 or 15 minutes finishing up this discussion, and then we do the summary class. I just wanted to, who is not going to be able to come tomorrow?
What time is
I
it?
see. 5:30. No, you can't, right? Okay. So, all right. So I think we're going to miss out on this part, but that's okay. We just don't have time, So, and by the way, we'll have a video, so I think you can, maybe catch up on that if you don't mind. So, anyway. Okay. I think we're out of time today. So, yeah. All right.